Welcome to the second semester of Organic Chemistry. In this video, we will apply the chemical principles learned in Organic Chemistry 1 to a complex problem. This complex problem is in biology. I've chosen a problem from biology since many of you are biology majors and all of you are human beings. So this should be of some interest to us. Really, this entire video is a ruse to recall and review reactions and principles of chemical reactivity, again, that were learned in Organic Chemistry 1, such as reactions of nonpolar pi bonds. By nonpolar pi bonds, I mean alkenes and alkynes, though in this video we'll just discuss alkene reactivity. For example, the epoxidation of alkenes. We will review the relative stability of carbocations and explain trends and carbocation rearrangements based on that stability. All right, let's do it. So I have a question for you. I hope that this semester you'll have many questions for me, but let's start with a question for you. Where does the cholesterol in your body come from? Write down your answer. Well, we're not together for me to hear what you have come up with, but many students say from their diets, from eggs or other foods that contain fats. Well, as it turns out, most of the cholesterol in your body actually comes from your body. It is synthesized naturally. In fact, 18 molecules of acetyl-CoA are converted in a series of enzymatic steps to cholesterol. Let's just get warmed up today by proposing a complete curved arrow mechanism for this transformation. So go ahead and write something down. Okay, just kidding. Don't pause. Don't do that. Ha ha. So funny, right? Have lots of jokes this semester. Well, funny, but also we can do this. And by the end of the semester, we will sketch out the steps in cholesterol biosynthesis. Here are some of the big steps. And today we will focus really here from the conversion of squalene, this linear series of alkenes, into linosterol. And then linosterol is converted to cholesterol. But we're going to zoom in here. And this should be pretty amazing to you. This fully linear molecule will be converted into, whoa, this tetracyclic steroid core with several stereocenters. And linosterol, of course, is formed enantiomerically pure as a single enantiomer in the body. All right, now that we're all excited, let's get started. So again, today we're going to focus on the conversion of squalene to linosterol. Amazingly, this transformation actually takes place in two enzymatic steps. One enzyme converts squalene into 2,3-oxidosqualene as a single enantiomer. So this is the 3 position. There's the stereogenic center. And then a second enzyme converts the 2,3-oxidosqualene into linosterol. Obviously not in a single chemical reaction, but in a series of chemical reactions that take place in that same enzyme. You may recognize the A, B, C, D ring system of the steroid. So 6-membered ring for the A, B, and C rings, and a 5-membered ring for the D ring. You may recognize all of the stereogenic centers in this molecule, so all the chiral carbons. Well, since there are 1, 2, 3, 4, 5, 6, 7 stereogenic centers in linosterol, there are 2 to the 7 possible stereoisomers of this molecule. But how many are made in the body? One single enantiomer. Truly amazing. We'll talk about the conversion of 3S, 2,3-oxidosqualene to linosterol in just a bit. Let's discuss now the first enzymatic step in the conversion of squalene to linosterol, and that is the epoxidation of squalene. The enzyme that catalyzes this transformation is called squalene epoxidase. Of course, with this ase ending, I know that this is an enzyme. The enzyme does use a cofactor, which is the NADPH coenzyme, and molecular oxygen. Now, what is the molecular oxygen doing here? What do you think? Yes, one of those oxygen atoms is actually what is incorporated into the squalene, so to make the epoxide. We've learned how to make epoxides in the laboratory. It's not with molecular oxygen as the oxidant. It is with a peracid such as metachloroperbenzoic acid. So a peracid refers to the oxygen-oxygen double bond in this. So it looks otherwise like a carboxylic acid. There's just that extra oxygen, so it's a peracid. Per means an oxygen-oxygen double bond. Okay, so this is a peracid. For MCPBA, the R group is metachlorobenzene. Okay, so here we go. Meta means there's this 1-3 relationship between the two substituents on the benzene ring. We may remember from the first semester of organic chemistry that epoxidation is a stereospecific reaction, meaning that different stereoisomers of the starting material yield different stereoisomers of the product. So we have these diastereomeric trans and cis alkenes. The transalkene yields the trans product. Sometimes this is referred to as anti. It means the two methyl groups are pointed in opposite directions. One methyl group is coming out of the page and one is going into the page. It is indeed formed as a racemic mixture. This is a chiral epoxide. And that is because oxygen can add to either the top face or the bottom face in a 50-50 mixture. Both of these attacks are equally likely, so you do get a 50-50 mixture of enantiomers. In this reaction, the pi electrons attack the weak oxygen-oxygen single bond, breaking the bond. The electrons in this bond make a double bond here. These pi electrons accept the proton, and then these electrons from the sigma bond make the second bond between oxygen and the alkene carbons. We can number these carbons just to point out that each of the carbons of the alkene ends up making a bond to oxygen in the epoxide product. And again, this attack can happen to the top face. It could also happen to the bottom face of the alkene, and that's why there's a racemic mixture. Now, when the cis alkene is treated with MCPBA, an epoxide product is formed. Just as before for the transalkene, the stereochemical relationship of the methyl groups is preserved in the products. They were cis in the starting material, and now the methyl groups are syn in the resulting epoxide product. However, this epoxide is achiral. There is a mirror plane of symmetry within this molecule. So although attack does equally happen to both the top and bottom face of this cis alkene, the two resulting products are exactly the same because this molecule is achiral. All right, well, hopefully that was a pleasant review of Organic Chemistry 1, and if you need to take some time and go and review that reaction, you certainly should do that this week. In fact, we should review as many reactions to alkenes and alkynes as we can possibly remember. Let's pause the video and list as many reactions of alkenes as you can. For a bonus, if you like, repeat the exercise for alkynes and then come back and join me. Well, I've listed a few here, and then frankly, I got tired of writing them down, but I did want to point out there are two big groups, reactions of alkenes via carbocation intermediates and those that are not via carbocation intermediates. So when you're doing your review of electrophilic addition reactions to alkenes and alkynes, please remember that organizing principle. Now, although in the laboratory with MCPBA, which is a nice achiral reagent, both enantiomers of chiral epoxides are formed. in squalene epoxidase, which is a heavily chiral, has a very defined three-dimensional shape and exists as one single enantiomer because it's made from one single enantiomer of amino acids. So this enzyme only epoxidizes one face of the squalene, making one single enantiomer of 2,3-oxidosqualene. Amazing, right? Well, what's even more amazing is the second enzymatic step, converting the epoxide to linosterol. Now, this second step is catalyzed by the enzyme oxidosqualene linosterol cyclase. The names are very rational. This enzyme folds up the 2,3-oxidosqualene in the perfect conformation, the perfect shape for to form these four rings and for a series of rearrangements that we'll talk about in just a moment. Now, the first thing that happens in this enzyme is that an acidic side chain interacts with the epoxide functional group in the 2,3-oxidosqualene. We can represent the enzyme as Ns. Think about an acidic side chain. So acidic means proton donor. That side chain interacts with the epoxide and donates the proton. So what I'd like for you to think about is, what will this molecule look like when the epoxide has been protonated? See if you can draw what belongs in that box. There are a few ways that you may have approached this problem. Let's draw in the epoxide here and protonate it. All right, so here we have a protonated epoxide. We can do a little bit of analysis of that epoxide. So there's a secondary carbon, carbon 3. Secondary means, of course, that carbon bearing the epoxide functional group. So here I'm just abbreviating a functional group as X, but that carbon is bonded to two other carbons, 1, 2, and then carbon 2 here is a tertiary carbon. Carbon 2 is bonded to 1, 2, 3 other carbons, just like here, 1, 2, 3. This is an example of a tertiary carbon. Where do we go from here? Well, we remember that epoxides are electrophiles, and protonated epoxides are quite electrophilic. So this species we predict to be electrophilic, or an electron-poor species, and to react with a nucleophile. There are two possible places where it could react: the carbon 3 oxygen bond or the carbon 2 oxygen bond. So a nucleophile may attack at carbon 3, or it may attack at carbon 2 and open up that ring in either case. Let's review what we know about epoxides and epoxide ring openings from Organic Chemistry 1. Epoxide openings happen under two different sets of conditions: either basic conditions in the presence of what is typically a strong nucleophile, or under acidic conditions with a weaker nucleophile, but via a strong or quite reactive protonated epoxide electrophile that is reactive enough to react with weaker nucleophiles. Which of these scenarios is most similar to the situation we're in with the protonated 2,3-oxidosqualene? Well, yes, an acidic side chain was used to protonate the epoxide here, so we should consider it acidic conditions. Before we go there, let's review both types of epoxide openings. Epoxides can be opened by nucleophiles due to the high level of ring strain associated with this three-membered system. The 60-degree bond angles in the epoxide deviate quite a bit from the ideal bond angle for sp3 carbon of 109.5 degrees. When the ring is open, that angle strain is alleviated, and ideal angles of 109.5 can be adopted in the product. Epoxides are electrophiles and can be opened by nucleophiles due to the polar carbon-oxygen bonds. We considered not only the electrostatic attraction between the electrons of the nucleophile and the partial positive charges on the carbons bonded to the epoxide oxygen. We also considered an orbital argument for why epoxides are opened in this fashion. Not only do epoxides have polar carbon-oxygen bonds, they also possess low energy empty molecular orbitals to accept the electrons from the nucleophile. The nucleophile donates its high energy electrons. The epoxide accepts those electrons into its low energy LUMO, its low energy empty orbital, which in this case is sigma star CO. You can see how properly they are aligned and how filling sigma star CO will break the sigma bond, eventually resulting in this epoxide opened product. Now that we remember the basics, let's review the two sets of conditions. Basic conditions refers to the strong or basic, often nucleophile. Acidic conditions refers to the presence of an acid catalyst, again generating this very reactive electrophile. Under both sets of conditions, the epoxide is opened, right? Under basic conditions, this bond is broken. It's no longer here in the product. It's been broken. And this bond has been made between the nucleophile and the primary carbon. Under acidic conditions, a different carbon-oxygen bond has been broken. This one, you see that there's no longer a bond here between the secondary carbon and oxygen in the epoxide opened product. And a carbon nucleophile bond has been made between the secondary carbon and the nucleophile. So with that analysis in hand, let's zoom in on epoxide openings under basic conditions, and then we'll get to acidic conditions, which will make a nice analogy to the problem we are currently trying to solve. Under basic conditions with a strong nucleophile, again, there are two possible electron pore sites in the epoxide. There is this carbon-oxygen bond and this carbon-oxygen bond. The difference between the two carbons bonded to the epoxide oxygen is their substitution pattern. There is a primary carbon and a secondary carbon. When the nucleophile attacks the epoxide, it is attacking in an SN2 fashion. The lone pair of the nucleophile forms the nucleophile carbon bond while the carbon-oxygen bond is breaking. I've drawn out the frontier molecular orbital analysis at the bottom of the screen. Because the approach of the nucleophile on the electrophile determines the energy of the rate-determining step, and in fact the only step of this reaction, attack occurs at the less substituted carbon. Because there are only hydrogens bonded to the primary carbon versus a methyl and a hydrogen bonded to the secondary carbon, it is lower energy or easier for the nucleophile to attack the primary carbon. If the less sterically hindered carbon, the less substituted carbon, the one that's attacked, is a stereocenter, then there will be inversion of stereochemistry, just like in all SN2 reactions. Of course, in this case, the carbon that is attacked, the less sterically hindered carbon, is not a stereocenter. So there's no inversion here. And the stereocenter, though that carbon was not attacked, so it just stays the same. Wonderful. Well, hopefully that's a refresher on basic conditions. Now let's review epoxide openings under acidic conditions, as we will make an analogy to what we learned about these types of reactions in Organic Chemistry 1 to what is happening to oxidosqualene in the problem at hand. Under acidic conditions, we mentioned that the epoxide is protonated by a strong acid catalyst, generating the protonated epoxide, which is quite electrophilic. We have learned that the more substituted of the two carbons in the epoxide, so the same two carbons, we have the primary carbon that was attacked in the SN2 type reaction under basic conditions, and then we have the secondary carbon. The more substituted of these two, the secondary carbon, it will actually share the positive charge with that electrophilic oxygen. So what does that mean? I'm going to redraw down here at the bottom of the screen. I will label this secondary carbon. So that carbon will share the positive charge with oxygen. We can draw this a couple of different ways. We could just think about splitting up the charge here. Now, how does this happen? Well, this would happen through this bond being lengthened and the electrons in that bond being pulled towards oxygen. And at an extreme, what we would see is the electrons in this bond just being fully localized on oxygen and a carbocation resulting at the more substituted carbon. So this is the extreme picture, right? This is the extreme way that the secondary carbon could share the positive charge with oxygen. It could just donate the electrons in the bond to oxygen and then assume the positive charge. So however we want to think about it, we know that the secondary carbon, look back at the top of the screen now, back to this picture. The secondary carbon is sharing the charge. It will be attacked by the weak nucleophile. So the weak nucleophile is attracted at electrostatics to that secondary carbon and will attack. So we can show that attack. You can see that this is an SN2 attack, just as under basic conditions. You can see that the nucleophile is donating the electrons in its highest energy molecular orbital, a lone pair, to sigma star Cx, so the LUMO of that electrophile. At the same time that the nucleophile carbon bond is forming, the carbon-oxygen bond is breaking. This is an SN2 reaction, a bimolecular nucleophilic substitution step. The weird thing is that it's happening at the more substituted carbon, and that's because under acidic conditions, there's that buildup of positive charge at that more substituted carbon. The nucleophile, the weak nucleophile, is attracted to that buildup of positive charge, and so it attacks the more substituted carbon. So weird SN2 just means this attack at the more substituted carbon. And again, that has to do with electrostatics, with buildup of positive charge. So weird SN2 attacks more substituted carbon, but because it is an SN2, there is inversion of stereochemistry. So S to R or R to S configurations. We can see that happening at the stereocenter because of this SN2 attack there. In our generic mechanism here, the species that results from the attack would be protonated, look like this, and then simply whatever the base base in solution will just deprotonate to generate the neutral product. Spend some time on your own comparing and contrasting epoxide openings under basic and acidic conditions. Spend some time on your own considering all the different nucleophilic species that may participate in both types of these reactions, because that affects what the functional groups are in the final products. So spend some time reviewing on your own. Together, let's try to apply what we've just reviewed about epoxide openings under acidic conditions to this problem of oxidosqualene. So here we are under acidic conditions. The enzyme uses an acidic side chain to protonate the epoxide. I should mention that there is no strong acid floating around in the enzyme. There's no sulfuric acid. There's no triflic acid or tosic acids. the organic acids that behave similarly to sulfuric acid. There are none of these strong acids. There's no HCl in the enzyme. The enzyme is using one of the acidic functional groups on one of the amino acids in that enzyme, positioned perfectly near the epoxide to protonate it. It's a marvelous, beautiful, amazing thing that we can all appreciate. This is happening with actually a weak acid and not a strong acid by the power of the enzyme. With that said, we are back here with the protonated oxidosqualene. And now we must consider what this species will look like electronically. So which carbon? Carbon 2 or carbon 3? And of course, I'm using the nomenclature numbering, so the number's in red, I'm not referring to the substitutions. It's a bit confusing because carbon 2 is a tertiary carbon, carbon 3 is a secondary carbon. But which of those carbons, carbon 2 or carbon 3, will share the positive charge with the oxygen of that protonated epoxide and thus be reactive? Yes, if you answered carbon 2, you are correct. Carbon 2 is more substituted than carbon 3. And thus it will share the positive charge with the oxygen. We could represent this by putting in a delta plus symbol next to carbon 2, or we could even break the bond between carbon 2 and oxygen and show the positive charge localized on carbon 2. So that's the extreme, right? Break the bond and show that positive charge localized on carbon 2. Or if you like, you can show the charge shared between oxygen and carbon 2. But nevertheless, no matter how you show it, we are predicting that carbon 2 will react with a nucleophile in whatever step is happening next. Cool, so what do we think is going to happen next? What is the nucleophile that's going to attack carbon 2? Make a prediction and then come back. Okay, did you write down your prediction of what will attack carbon 2? It may have been difficult to predict what will happen next. If we're trying to make an analogy to the epoxide openings that we learned in Chem 12A, we might be looking for a nucleophile with a lone pair of electrons to open up the epoxide. However, when we take a look at species 1, which is the protonated oxidosqualene, this species, which we can represent two different ways. We had just represented it as a protonated epoxide with the charge shared. But at an extreme, we said we could also represent this where that carbon 2 oxygen bond is completely broken and this carbon is bearing the positive charge. What do we call a species like this? Yeah, we call it a carbocation. And since we have really no idea what species number 1 is going to do, it's going to be dramatic, right? Look at all these rings that are formed. We can see all the rings in the prosteryl cation that are formed. Whoa. But maybe we don't know what's going to happen next because we don't see a nucleophile with a lone pair. And so we're having a hard time making an analogy to the epoxide openings that we know. So what do? We need to think more about carbocations. And then perhaps we can figure out what in the world it happens to convert species 1, the protonated oxidosqualene, to the prosteryl cation, which will then be converted to linosterol. So with that in mind, let's take a moment and review carbocations. Pause the video, draw a carbocation, and list as many facts as you can about that carbocation. Please don't skip this step. Go ahead and do it. Okay, if you didn't draw a carbocation, here's one that you can use. So pause and list some facts about this carbocation that I've drawn, if you haven't done it on your own already. Okay, well, I've drawn the carbocation 2 different ways here. I have drawn in the hydrogen that is implied on this carbon. A few facts we can list is that there is a positive formal charge on the carbocation carbon. That carbon has an unfilled octet. There's only 6 electrons about that carbon. 2, 4, 6. That means the species is electron poor. It will act as an electrophile. You may have listed that the carbocation carbon is sp2 hybridized with a planar geometry. In fact, I'm going to move over to this representation. This carbon, and this hydrogen, so everything bonded to the carbocation carbon, occupies the same plane. So all 3 of those atoms occupy this plane, the plane of the page. You may have written down the bond angles. There are 120-degree bond angles. And because this carbocation carbon is sp2 hybridized, it has 3 sp2 hybrid orbitals with which it can make sigma bonds. It's making all 3 of these sigma bonds with those coplanar sp2 orbitals that are arranged 120 degrees from each other. And then it is left with 1 p orbital that was not hybridized, and this p orbital is empty. So if I imagine rotating this species, so now all those sigma bonds are perpendicular to the plane of the paper, that empty p orbital will be in the plane. This p orbital is the LUMO, the lowest energy unoccupied molecular orbital of the carbocation, and it can accept electrons if it reacts with some nucleophile or some species that has electrons to donate. And did you write any other facts down on your paper? Last time I did this exercise in class, students said that carbocations may rearrange. And I'll just go ahead and write that down, and we will come back to that later. Excellent. So the carbocation has that empty p orbital with which it can accept electrons. So now, does that help us? Are there any electrons around that the carbocation can accept? Yes, these pi electrons. We can see in the prosteryl cation that there are no pi bonds. So those electrons are going to be doing something. We already know that pi electrons can be donated to electrophiles. Pi electrons represent the highest energy occupied molecular orbital for alkenes. And we do know they undergo electrophilic addition. We talked about it earlier, right? We talked about it earlier with epoxidations. The epoxidation of squalene was an example of an electrophilic addition. And we reviewed epoxidations, and we said we need to review all the electrophilic additions that we learned in Organic Chemistry 1, and we started to make a list, and you'll finish that review on your own. But pi electrons do serve as nucleophiles. And for those reactions that proceed via carbocations or carbocation-like intermediates, the most stable carbocations will be formed, as the most stable carbocation will represent the lowest energy pathway, and the universe proceeds via the lowest energy pathways spontaneously. And that includes the conditions of this transformation. The enzyme squalene linosterol cyclase is holding the species in the perfect conformation for these electrons in the pi bond to attack. One of the carbons of the pi bond will make a bond to the carbocation carbon, and the other carbon will be left as a carbocation. So try to draw the results of what we just described, and then come back and let's look at it together. It is the secondary carbon of the protonated oxidosqualene. I'm calling this molecule species 1. It is that secondary carbon that makes the bond to the carbocation carbon. So here's the new bond. This was the secondary carbon, and that leaves the tertiary cation. This happens for two reasons. First, because the epoxide is holding squalene in the conformation where this is the bond that is formed. Okay, so first, just the conformation of the molecule in the enzyme. But the second reason why the tertiary carbocation is formed and the secondary carbon is the one that makes the bond has to do with carbocation stability. So we're going to pause again and review carbocation stability. Before we do, I'm just going to show you, look, one of the rings of the steroid has been formed. We formed the A ring, right? So this whole transformation, species 1 to linosterol, this is all happening in this oxidosqualene linosterol cyclase. So there's the protonation by the acidic side chain. Then all 4 of these rings are formed, and that's what we're working on right now. And this is going to occur by a series of electrophilic addition reactions to the alkene. So the alkenes are going to react with electrophiles. Well, here are the alkenes that are doing the reacting. And we said the carbocation, that is the electrophile. So electrophilic addition reactions to alkenes. Those reactions will form the A, B, C, and D rings. And then this last arrow, what's going to happen here? Well, here we're going to have carbocation rearrangements. Beautiful cascade of hydride and methyl migration. So carbocation rearrangements to convert the prosteryl cation to linosterol. All right, so right now we're making the rings in the series of electrophilic addition reactions. And since carbocations are being formed in this process, as we just saw here, let's take a break and discuss carbocation stability. Go ahead and rank the following cations from least stable, which means highest energy, to most stable, which means lowest energy, and then explain your answer. Okay, make sure you have that written down. Now, let's describe the trends in carbocation stability. There will be 2 trends that we should be keeping in mind as we make our rankings in the previous question. Yeah, so the first is substitution pattern. So is the carbocation carbon tertiary? Is it secondary? Is it primary? Is it methyl? Where tertiary cations are lowest energy or most stable, and methyl and primary cations are least stable, which corresponds to highest energy. Okay, we'll just draw quick examples. This would be a tertiary cation, a secondary cation, a primary cation, and the methyl cation. What's this? Okay, so this is a tertiary cation because it's bonded to 1, 2, 3 carbons. 1, 2, 1. I'll quickly remind you why the tertiary carbocation is more stable than the secondary and the primary. The Y has to do with an effect called hyperconjugation. So we know that cation has this empty p orbital. Adjacent methyl groups or alkyl groups can donate or share just a tiny bit. They can share electrons from sigma CH or sigma CC bonds with that empty p orbital on the carbocation. So this is called hyperconjugation, and if you want to review it or learn about it for the first time, please look it up in your book. All right, but the trend here is substitution. More substituted cation is more stable. This also explains why we said in the protonated epoxide, the more substituted carbon is going to share the positive charge. Well, why? Yeah, because positive charges, cations are more stable on more substituted carbons because of the hyperconjugation from their alkyl substituents. Now, the second trend in carbocation stability is delocalization of charge, so pi delocalization. In other words, full conjugation. For example, the allyl cation might look primary and unstable. However, there are pi electrons adjacent to that empty p orbital. So there is a resonance structure that can be drawn. This charge is actually spread out and shared among all 3 atoms. So this is the most stable cation on this page. Generally, drawing resonance structures which represent conjugation or delocalization of charge, that effect, full conjugation, is a more significant effect than hyperconjugation, substitution. So trend number 2 is more significant. It's more important, it's more stabilizing than just substitution. So having more alkyl groups. Keeping that in mind, let's review your rankings. And if you didn't answer this problem when I asked you to, go ahead and try to answer it now, keeping in mind what we just discussed. You could also revise your answer, keeping in mind what we just discussed. Right, go ahead and pause. All right, cation 1 is secondary, cation 2 is tertiary, cation 3 is primary, cation 4 looks primary, but we see this adjacent pi bond. This is one of the patterns we can look for to signal to us that a species can be described by resonance structures, showing that this charge is actually spread out on all 3 of these atoms. The charge is shared. So carbocation 4 will be lowest energy due to delocalization of charge. Carbocation 2 is the next lowest energy because it is tertiary. Carbocation 1 is the next lowest energy because it was secondary. And carbocation 3 was the highest energy or the least stable because it is primary. All right, make sure you have this down before you revisit the cyclization of the protonated oxalosqualene with me. All right, so here we are. We're in this part of this single enzymatic step all the way from 2,3-oxidosqualene to linosterol. It's amazing that one enzyme can catalyze this transformation. And we are right in here to this series of electrophilic addition reactions, converting species 1 to prosteryl cation. We looked at the first electrophilic addition that establishes the A ring. And that cyclization leaves this tertiary cation. Now that tertiary cation we know is electron poor. It's a carbocation. It's an electrophile. Has that empty p orbital that can accept electrons. And look what is right next to it, held in the perfect conformation by the enzyme. Yes, there is another pi bond. That pi bond donates its electrons to that carbocation. Now, one of the 2 carbons of that alkene will be left with a positive charge, and one of them will make a bond. So we can see that it is this carbon that makes the bond. Here's the bond. And the carbon I'm going to represent in pink, this carbon is left with the positive charge. It's left as a cation. We can understand why that happens because the carbon that makes the bond is the secondary carbon. The carbon that's going to be left with the positive charge is tertiary. So there's a tertiary cation here, which will be more stable than a secondary cation. Awesome, that cyclization establishes the B ring. And there's a new carbocation that can react with, yes, the next alkene, so this alkene, to establish the C ring of linosterol. So now these pi electrons from this alkene are donated to that empty p orbital on the carbocation. That will fill up the octet of the carbocation carbon, close the C ring, and generate a new cation. Okay, so we have these 2 carbons. We have the secondary carbon of the alkene, and we have the tertiary carbon of the alkene. We would expect that the tertiary carbon would become the cation, and the secondary carbon would form the bond, right? But if that happens, there would be a 5-membered ring. Yikes. What size was the C ring? Do you remember? Well, the C ring is a 6-membered ring. So, all right, well, what happens? Well, lots and lots of research has been done on this entire pathway, so the steroid biosynthesis. Lots and lots of research, Nobel Prizes have been won. And it is believed that the first thing that happens actually is what you would expect based on energetics, that the secondary carbon makes the bond, so that makes a 5-membered ring, leaving the tertiary cation. And then the enzyme facilitates, this bond shifting over, forming the 6-membered C ring and the less stable secondary cation. So a less stable or higher energy cation is formed. And of course, that is facilitated by the enzyme. So it is believed that first this species is formed with the more stable tertiary cation, and then the ring expands to form the less stable cation, but the 6-membered C ring. So the enzyme is thought to facilitate this transformation to a higher energy cation. Very cool. We haven't seen that before. Usually we see carbocations rearranging to form more stable cations. Here we see it forming a less stable cation. And that's facilitated by the enzyme. It is holding the molecule in the shape that's appropriate for that. Okay, so where are we now? Now we are at species 5 here. Species 5. The series of electrophilic additions has established the A ring, the B ring, and now the C ring. And that was a bit funky. It left us with the secondary cation. And now what do you think is going to happen? Yes, establish the D ring. So that's going to happen now. So we're going to zoom in here. And this is the last step that has to occur before the prosteryl cation is formed. So we have, once again, the electrophilic carbocation. It has that empty p orbital, and the enzyme is holding this alkene with its pi cc electrons that it can donate in the perfect place for this cyclization to occur. So let's go ahead and show that. So these pi electrons are going to be donated to the carbocation. That's going to close the D ring. It's going to make this bond right here. It's going to close the D ring. And so the 2 carbons of the alkene, this one makes the bond, and then the secondary carbon makes the bond, and then the tertiary carbon of the alkene is left as a cation. But as we know, tertiary cations are the most stable substitution pattern for a cation, so we expect that to be energetically favored. All right, we did it. This series of electrophilic additions, series of cyclizations, has closed the A ring, the B ring, the C ring, and the D ring. And it seems so simple, right? Wrong. We also didn't point out that several stereocenters were set. So we see all these stereocenters being set. There are many different possible stereoisomers of the prosteryl cation, and only one is formed as a single enantiomer because of the shape of the enzyme. So when you hear biologists talk about structure and function, this is a great example. The structure of the enzyme directly affects which stereoisomer of the prosteryl cation is formed. And if the enzyme had a different shape, this entire reaction would not happen. So structure determines function of enzymes. All right, we are almost there, folks. Let's take a look where we are. So we saw that this series of electrophilic addition reactions where alkenes were attacking carbocations established the A, B, and C and D rings. So now for the prosteryl cation to be converted to lanosterol, what do you think needs to happen? Just take a minute, pause, and try to write down or note the differences between the prosteryl cation and lanosterol so we can think about what is going to happen and how it might happen. What did you come up with here? All right, well, let's compare. So here we can see where the carbocation is in the prosteryl cation. In lanosterol, there is a hydride or hydrogen atom here. A stereocenter has been set. Now this methyl group is a substituent at a stereogenic center. So not only do we need to have a hydrogen here, when the stereogenic center is formed, the methyl group only goes down. Of course, Down and up depends on how this chain is rotated. So let's go ahead and assign R or S to the stereocenter. Since R and S absolute configuration doesn't change. All right, we're looking at the atoms bonded to the stereogenic center. So carbon, hydrogen, carbon, and carbon. Assigning them priority based on atomic number. Hydrogen is the lowest atomic number. It gets the lowest priority. So priority 4. Now, carbon, carbon, carbon is a tie, so we look at what's bonded to those carbons. On the methyl group, there's 3 hydrogens. On this carbon, there is 1 carbon and 2 hydrogens, so that's CHH. On the other carbon atom bonded to that stereogenic center, there is carbon, carbon, hydrogen, so CCH. That means that this carbon has 1. This carbon has 1. It is priority number 1. This carbon is priority 2. The methyl group is priority 3. Now we are going to trace the path of the substituents by priority. So 1, 2, 3. 1, 2, 3, right? That path is going in a counterclockwise direction, which would be S. However, the lowest priority group is coming out of the page. It's supposed to be going into the page for this convention, the RS convention. So all that means is it's opposite day. This is actually an R stereocenter. All right, fun review. If any of that was Greek, go ahead and review how to assign RS configuration to stereocenters. Okay, so from the prosteryl cation to linosterol, this stereocenter is set, and there's a hydrogen that now bonds to the carbon that was the carbocation carbon and the prosteryl cation. What else happens? Well, let's see. This hydrogen is now suddenly a methyl group. That looks like magic, but it's not. All right, in linosterol, there was a methyl down, and the prosteryl cation, there is a methyl up. In linosterol, there is an alkene where there is a methyl group and a hydrogen on these 2 carbons at the BC junction. So there are many differences between the prosteryl cation and linosterol. This transformation represents a series of carbocation rearrangements. So before we attempt to propose a mechanism, which we will for this conversion, let's just review carbocation rearrangements, right? The prosteryl cation, it's a carbocation, and it's going to rearrange, and that's going to give us linosterol, but it's not just one rearrangement. It's going to be multiple rearrangements. So let's just review a simpler example of a rearrangement first. By simple, I don't mean easy. I just mean in a smaller molecule. If you'd like to try this example on your own, please pause and do so. If you're exhausted because we're 52 minutes into the lesson, just, follow along. It's up to you. We're asked to predict the product of this reaction. So what I'm going to do is I'm going to identify functional groups. I'm going to ask all species what they are. I have identified an alcohol and a strong acid. So I might have activated my knowledge of my reaction chart in my brain by just labeling those things, and I might know that an alkene functional group should result from this reaction, or that's what I would predict. I also might not remember. So let me pretend I do not remember and work through the mechanism and just model to you what you might do if you have forgotten, or for some reason, you can't activate that knowledge, how you can try to solve the problem with your chemical intuition. Sulfuric acid is a strong acid. It's going to protonate something. The only thing that sulfuric acid can protonate here is the alcohol. So it's protonating the lone pair of the alcohol. The alcohol will act as a base, donating those non-bonding electrons on oxygen to the proton on the sulfuric acid. So it'll accept that proton. The product of the proton transfer reaction is simply a protonated alcohol. Well, where did it go from here? Well, protonated alcohol has a pKa of about -2, so perhaps it donates the proton and we go back to the starting material. But that would be boring, and probably the starting material is not the product of the overall reaction, so let's try to keep going. We know that water is a good leaving group. So perhaps some sort of SN1 or E1 reaction occurs. Perhaps water leaves, so a heterolysis occurs, a bond is broken. When that bond breaks, a secondary cation is generated. Secondary carbocations are intermediate in energy, so this is reasonable to propose generation of a secondary cation. Now we might just keep going here. We might look for a nucleophile or look to eliminate a beta hydrogen from this cation to either get a substitution product via an SN1 or an elimination product via an E1. However, whenever there's a cation, we should be looking out for carbocation rearrangements. There are 4 patterns of carbocation rearrangement that you will review as part of your Organic Chemistry 1 review. And this substrate represents one of those patterns. There is a secondary cation adjacent to a quaternary carbon. So instead of this cation reacting with some external reagent via SN1 or E1 pathways from here, what happens instead is one of these methyl groups on that quaternary carbon migrates over or shifts over, generating now a tertiary carbocation, which we know is more stable than a secondary carbocation. So typically when we observe carbocation rearrangements, it's because a more stable species is formed. So tertiary cations are more stable than secondary. Again, one of these methyl groups, I'll go ahead and just write CH3. It's moved over, it's now bonding to carbon 3. So there's been what we call a skeletal rearrangement. The connectivity of the carbon skeleton has changed. There used to be 3 methyl groups on carbon 2, but now there's only 2 methyl groups on carbon 2, and a methyl group has moved to carbon 3. So it's a carbocation rearrangement or a skeletal rearrangement. Different words for the same thing. From this more stable cation, either SN1 substitution could happen if there was a coordination of some nucleophile. Then we might observe SN1, or there could be an elimination, and then we'll see an overall E1 product. In this case, there are no nucleophiles. Coordination, this pathway, would require some nucleophile X minus to attack the carbocation, and there is no nucleophile. There's the conjugate base of sulfuric acid, but it is not very nucleophilic, and I probably should have written it in, so let's write it over here. So we do have the conjugate base of sulfuric acid. It's an extraordinarily weak base and it's not very nucleophilic. So it is not going to attack. We are not going to see a substitution product. But an elimination will occur and we will observe the elimination product. So there is a proton at carbon 3. So we want to look adjacent to the carbocation carbon. So looking at this species here. There are 2 carbons adjacent to that carbon, carbon 1 and carbon 3. Look and see, do they have beta hydrogens do they have a hydrogen that could be eliminated? Yes, both of them have hydrogens, but the hydrogen from carbon 3 will be eliminated rather than carbon 1 because this will form a tetrasubstituted alkene, which is more stable than the monosubstituted alkene that would have been produced if, say, this hydrogen had been removed on carbon 1. And we do see the most stable alkene product formed from E1 eliminations. Okay, cool. That was a lot to process. Please process it. But what I'm trying to remind you of here is carbocation rearrangements. They occur when a more stable cation can be formed. One of the patterns that you'll be looking out for is quaternary carbons adjacent to secondary cations, because when an alkyl shift occurs, a more stable tertiary cation can be formed. You will review all 4 of these patterns in your Organic Chemistry 1 review assignment. But let's get back to our problem. All right, let's get back to our problem in hand. So we have the pro-steryl cation being converted into linosterol. All right, there is this hydrogen. Where do you think that hydrogen comes from? Yes, it's this one. So this hydrogen migrates over, okay? So it migrates over, it stays on the bottom face. I know it looks like it jumped up to the top. That's because these pictures also have bond rotation occurring around this bond. But that hydrogen migrates first. So the first thing that's going to occur is a hydride shift. So that's number one, hydride shift. Now, I am going to show you how all this works and actually in a 3D representation, but maybe we can plan it out right now before we look at the 3D representation. Then you can have these two-dimensional 2D representations by your side while you're watching me work in 3D. So that hydrogen is going to shift. There's going to be a hydride shift here, which is the type of rearrangement. That's going to leave a carbocation here. Okay, so this carbon right here, that's going to be a carbocation. And we can see that now that hydrogen needs to bond to it. So where do you think, because this hydrogen right here in yellow, that's not this one. It's moved. It's here now. So there, imagine there's a carbocation now at the yellow carbon. So where do you think that this hydrogen comes from? It has to come from adjacent to that carbon. So it's this one. And it's that one because remember we said, oh, it magically turns into a methyl. No, it does not. The hydride moves, so now it's going to shift over here. Now it's there. Okay. And then that is going to leave a carbocation at the carbon that hydrogen was bonded to. So the one that now magically has a methyl group in linosterol, it's because the hydride moved away. Okay, now where does that magic methyl group come from? Where do you think that methyl group came from? Yeah, it's this one. You're like, oh, it moved from up to down. No, this methyl group is going to move over here. There's going to be a carbocation at this carbon that it was bonded to. That carbon will be a carbocation. And then somehow this methyl group is going to move over there. All right, so this one's going to shift over. And then so this methyl group shifts to this carbon. Here it is in linosterol, right? That is going to leave a carbocation here. And then this methyl group in linosterol, that is going to come from here. This methyl group in the prosteryl cation is going to scooch over and fill up that empty orbital on the carbocation that's going to be there. So it's going to move over here, and then there it is. That, of course, is going to leave a cation here, right here, but that's perfect because there could be an elimination, which just means this could become deprotonated, like we did with sulfur, like we did in the previous example when we were talking about rearrangements. So this could be via an elimination. All right, it's an alkene. All right, that was a lot. It's going to feel like even more when I write it in the 3D representations. Let's write out the list of what we're going to do. So first there's going to be that hydride shift. Then there's going to be another hydride shift, followed by this green methyl. That's going to migrate. So the methyl migration, a methyl shift. I'm going to call it a migration. Same thing, it's carbocation rearrangement. Followed by another methyl. So now this methyl group, this one, moves over. That fourth methyl migration, that fourth step, that leaves a carbocation here at that purple carbon. And so there will be an elimination, removing this proton to get the alkene. So the last step is elimination, deprotonation, right, to generate the alkene. All right, that's it. Awesome. So let's draw it out in the 3D structures, and then we will know how this amazing enzyme takes 2,3-oxidosqualene all the way to linosterol by this series of electrophilic additions, of cyclizations, and then carbocation rearrangements. As promised, here's the 3D pictures. Again, we're showing how the prosteryl cation is transformed to lanosterol. These are the 2D pictures we were just working from. And now we're going to look in 3D. The overall transformation is in this box, and it's going to occur via these steps. The first step is the hydrides shift that establishes the R stereochemistry on that side chain. So let's go ahead and write it on our 3D representation here. So this is the hydrogen. So we have that hydride shift. That's the first step. That generates a carbocation where that hydrogen used to be, right? Now there's an unfilled octet there, a carbocation. The next step is another hydride shift, right? The one in orange. So now there's another hydride shift. Fill up that unfilled octet on that carbocation. So that hydride is actually this one. I didn't draw it in my structure, but this pointed down. That's this one, down, right? As indicated by the dashes. Zoom back in here. So now this migrates. So second hydride shift. That will leave a carbocation at the carbon that hydrogen was bonded to. Now it's a carbocation, right? So what next? Here, let's look at where we are. So on our plan, it was hydride shift. So the hydride shift established that R stereocenter on the side chain, followed by another hydride shift. So this hydride moves here. That was going to leave a carbocation on the carbon that is highlighted in orange. And then there needs to be 2 methyl migrations. All right, so let's go back. Okay, here we are. Now this methyl group migrates over. That is going to leave a carbocation at that carbon. So we can see the methyl group migrated from this carbon, and now it is a carbocation. There's one final methyl shift. Moves over. Okay, so it moves over here. Here it is after it's moved. And that is going to leave a carbocation at that BC junction. So now all that's left is to install the alkene. So this time, a basic side chain or water in the enzyme pocket is going to deprotonate. The electrons in that carbon-hydrogen bond form a double bond between that carbon and the carbocation carbon, forming the double bond in lanosterol. So not so bad. 2 hydride shifts, 2 methyl migrations, and then an electrophile elimination, so deprotonation, right, where the electrophile here is a proton, to form an alkene. And that is how the prosteryl cation is transformed to lanosterol. We did it. From 2,3-oxidosqualene and that series of electrophilic addition reactions where the alkenes donated electrons to the cations and closed up all those rings, made the A ring, made the B ring, the C ring, and the D ring. And then the series of carbocation rearrangements to that prosteryl cation formed lanosterol. And this is all chemistry that you know from Organic Chemistry 1. So you learned a lot, right? So today we tackled this part of cholesterol biosynthesis. In our very last class, you will see this slide again, and we will tackle the rest of it. We have quite a while to go before we do that, but we will come back to this, don't you worry. For the final transformation for lanosterol to cholesterol, there's quite a bit. You can see both of these methyl groups are removed. In cholesterol, those are hydrogens. That looks fun. We can also see there's an isomerization of the alkene. And finally, hydrogenation of this alkene, from lanosterol to cholesterol. So quite a bit to do there. Actually, there is one more methyl that is removed. I didn't write it down. So this methyl also is not there in cholesterol. So lanosterol is converted to cholesterol, and then cholesterol can be converted to several different other steroids. And is probably happening right now in your body this moment as we speak. So cool. All right. So where does the cholesterol in your body come from? Your body makes it. It is biosynthesized. For most people, it doesn't matter how much cholesterol you eat. Your body regulates the amount of cholesterol in it, and it's making it itself. So for most people, unless they have some sort of biochemical disorder, eat all the cholesterol you want. It doesn't have any effect on how much is in your blood. Make sure after every class you take time to summarize what you learned and what questions you still have, and how what you learn relates to prior knowledge, things you have learned either in this class or in other classes. Be sure that you ask me any questions that you have. After every class, please revisit the learning goals. Be sure that you now know what I mean by them, and you can make problems for yourself or problems for people in your study group based off of them. So maybe now you go write a bunch of practice problems for your friends all about remembering reactions of nonpolar pi bonds. Or I asked you to go and revisit the 4 patterns in carbocation rearrangements, for example. We didn't discuss them in this video, so you have to go back and do that on your own. Very last thing, make sure you spend some time this week setting goals for Chemistry 12B and discuss with me how you might meet those goals. All right, this was fun. Make sure you do your practice problems. Hopefully this sets you up to remember all kinds of things that you have forgotten between Organic Chemistry 1 and today, but now you can remember them.